Boa tarde. Gostaria de agradecer a presença de vocês nessa sessão extraordinária em homenagem ao Jacob Palis. A gente vai ter, deixa eu introduzir o nosso speaker, Marcelo Viana. Todos vocês conhecem. Primeira vez que eu soube sobre ele faz quase 30 anos. Estava andando pelos corredores do IMPA e um colega de mestrado me falou: aquele ali é o futuro do IMPA. E é verdade. E o Marcelo Viana trabalha na teoria do caos, sistemas dinâmicos, né, o nome oficial, que trata da imprevisibilidade. E a gente vê que nem tudo é caótico, porque o cara acertou a previsão. Marcelo Viana é o diretor do IMPA, tem uma história de trabalhos, contribuições para além da pesquisa matemática. Trabalhou com a União Internacional de Matemática, ele trabalhou com o Progresso da Matemática Latino-Americana, ele tem dado continuidade aos trabalhos que o Jacob teve, então é uma pessoa indicada melhor indicada para dar essa palestra. Sobre suas contribuições matemáticas, estão reconhecidas, falar seus trabalhos sobre a transformação de Henon, parcialmente hiperbólicos, a teoria, basicamente empurrando aqui para os trabalhos sobre a compreensão estocástica dos sistemas determinísticos e estudos de cociclos, expoentes de Lyapunov, etc. Muita coisa mesmo. Foram reconhecidas com palestra, por exemplo, no Congresso Internacional de Matemática, palestra plenária, e muitas outras coisas, como, eu creio, eu não preparei, não sabia que tinha que preparar, mas eu creio que o Prêmio Ramanujan, a Medalha da Malka, são muitos. Então, terminar aqui, dar a oportunidade do Marcelo fazer a homenagem, começar a homenagem ao Jacob. Obrigado, Marcelo.
Muito obrigado, doutor. Obrigado. Bom, é um momento muito especial. Eu vou pedir a licença de vocês para passar para inglês na apresentação, porque nós temos vários convidados que não falam português. I had a friend who knew much more than me about birds. And once he explained me that in some species of birds, there are individuals, and they are kind of unpredictable, which are very much praised, very much valued, because they can sing, they sing very well, but that's not what makes them special. What makes them special is the fact that they are capable of making the other birds sing. The presence of one of these individuals spreads the capacity for beautiful singing in the whole bunch of birds. And the person we are honoring here today, Jacob Palis, was such an individual. I don't have the time to speak about all the things he did that Arthur hinted at, so I will focus strictly on talking about his mathematical work, but I will also try to express this idea that these songs that Jacob sang contaminated the environment, and so I will also mention a few of the other songs that were played because of him. Jacob Palis was born in Uberaba, Minas Gerais, 15th of March, 1940. He graduated in the School of Engineering here in Rio. The university at that time was called the University of Brazil. Now it's the Federal University of Rio. Then he went on to the United States to get his PhD under the advice of Stephen Smale, who was a rising star in the international mathematical scenario, and would actually get the Fields Medal for proving the Poincare conjecture in higher dimensions in 1966. Jacob wrote a thesis entitled On Morse-Smale Diffeomorphisms, and I will talk about it in a little while. Then he came back. He came back to Brazil at a time where it didn't really make much sense to come back. He had a very promising career ahead of him in the US, being the first graduate student of a Fields medalist, graduating from the University of California in Berkeley. But he decided to come back and to help develop the country, and he dedicated his life to it, developing math in Brazil. He joined in 1969. He was director for 10 years, between 1993 and 2003. It was 10 years. Perhaps the greatest achievement of his administration was moving IMPA from being a strictly public institute to getting another, a different type of legal existence, which made possible, it's called Organização Social, which made possible many of the things that happened since in the last 25 years or so. In 2015, he retired at 75, compulsory retirement, and he became a researcher emeritus, which meant that he had all the rights, all the privileges of being faculty member, but didn't have any of the obligations. During his career, he supervised 41 PhD students from all these countries. And according to the Mathematics Genealogy Project, which is a database held nowadays by the American Mathematical Society, he has currently 347 academic descendants. Those are the students, etc. Now he has at least great-grandchildren, academic great-grandchildren, and they all add up to 347 researchers that were trained in his genealogy. A quick search in the MathSciNet database of the American Mathematical Society gives this information. He published 74 papers, has about 2,800 citations, and many other informations. He published consistently in the most exclusive journals in the area, Annals of Mathematics, Publicação Matemática e Achoes, Acta Invenciones. Had many co-authors. His favorite co-authors were Sheldon Newhouse, Loris Stakens, Jean-Christophe Yocos, Carlos Gustavo Moreira, and others that are present here. Exactly 25 years ago, I organized a conference here at IMPA to celebrate Jaco's 60th birthday. And I asked his friend and colleague, Sheldon Newhouse, to do the job that I'm trying to do now, to speak on Jaco's work. Sheldon did a very good job, but at the end, he told me that he had been able to speak about 1/3 of what he had prepared, which is, of course, a warning for me. Fortunately, we recorded the lecture, so I asked a graduate student to listen to all the lecture and write down the words of Sheldon. And then I revised that and helped Sheldon complete it. And that became a paper which appeared in Asterisk, entitled On the Mathematical Contributions of Jacob Palis. And this is the table of contents. This is a list of major topics. One thing that I found curious, I had forgotten it, I went back to reading it, is that there's a final section called Many Other Results. And among these many other results is, for example, the study of rigidity of centralizers, which was mostly done together with Yoko's, and is quoted in Yoko's nomination for the Fields Medal. So amongst the many other results of Jacob is Fields Medal material, which I'm not going to talk about today because there's no time for it. So I want to highlight three main areas where Jacob made major contributions. One corresponds basically to the beginning of his career. And it goes under the umbrella title of global stability. Then I will mention some of his results in bifurcation theory with various collaborators. And then, if I still have the time, I will talk about many of the proposals that Jacob was making starting from the mid-1990s that he called a global view of dynamics, which influenced a large number of people. Okay, global stability. Let's start. This is the setting, the mathematical setting. We have a manifold and a smooth manifold, any dimension in principle. And on this manifold, we consider both vector fields or transformations, smooth transformations, diffeomorphisms. And one of the novelties in the approach that was pioneered by Steve Smale and then Jacob pushed forward was to look at the space of all these. It's very much in line with ideas of Poincaré, to look at the space of all these systems, of all these diffeomorphisms, of all these vector fields with a topology, CR topology. And back in the 1930s, two Soviet scientists, Andronov and Pontryagin, had proposed a notion. They called it something different. Nowadays, we call it structural stability. Structural stability means that your law, the law of your system, if you change it slightly, if you modify slightly the parameters in your vector field or the definition, the formula for your diffeomorphism, the impact of that on the dynamics is not important. Essentially, the dynamics remains the same, doesn't change if you do that. So they defined this in 1937, and for at least 20 years, there were no examples there was no theory, no understanding of this notion. There's a definition, but you don't know what to do with that. Until in 1953, Maurício Peixoto, 1953 is 1 year after IMPA was created, but IMPA was created with a library, and Peixoto loved to go to the library, so he was going through a journal that had just shown up, and he read something about this notion, and he became interested. By the end of the decade, he had been able to come up with one of the major pioneer theorems in dynamics. He considered vector fields on the surface with a few simplifying assumptions. The first one is that the vector field has only a finite number of critical elements. The critical elements are the stationary points, the zeros of the vector field, or the periodic solutions. Then there should be no settled connections. The technical meaning of this is not so important. And also, the critical elements should be the limits. Every solution of the vector field should accumulate on one of the critical elements. And Peixoto proved that for this class of vector fields on surface, on an orientable surface, first of all, every such vector field is structurally stable. And this is the first serious example for the notion that had been introduced by Andronov and Pontryagin. And secondly, the set of all these vector fields is open and dense. Now, for those of you, what does it mean, open and dense? It means that if you have one of these vector fields and you modify it, it remains good. That's the openness. And if you have a bad one and you perturb it, it may become good. That's density. Okay? So in a sense, this means that the vast majority of vector fields on orientable surfaces are structurally stable, belong to this class, and so they are structurally stable. Around that time, Peixoto and Elon Lima met with Stephen Smale, who, as I said, was a rising star. He was a topologist, and he immediately became interested in what Peixoto was doing, and he generalized this class. I'm not going to write down the precise condition, but he thought of a much more general class of dynamical systems with the same flavor, but this time not just in surfaces, on any manifold. He didn't give it a name, but René Thom coined the expression Morse-Smale systems for this class that's Smale-defined. It was inspired in Morse theory, so the denomination makes sense. And Smale, very boldly, this was his very first paper on the subject, he knew basically nothing about the subject. He conjectured that just as in Peixoto's theorem, every Morse-Smale system is structurally stable, and they form an open and dense subset of all dynamical systems on any manifold. It's a very dramatic story. The density part was famously wrong, it was false. These systems are not dense, but all the rest was true. And the person who proved it was true was Jacob. That's his thesis on Morse-Smale diffeomorphisms. He proved that for any compact manifold, the subset of Morse-Smale systems is indeed open, and most importantly, non-empty. Open and non-empty, so on any manifold there's at least one of these, and all of these Morse-Smale systems are structurally stable, both if you look at vector fields or diffeomorphisms. So both continuous time and discrete time. Now, I have no intention of saying anything about the proof, but I do want to say a couple of sentences, because the method that Jacob introduced for proving this turned out to be very fruitful in many other situations, and I will come back at least once or twice during the lecture. It was known by then, by a theorem called the Hartmann-Grobman theorem. It was known by then, so proving structural stability is about proving conjugacy, about proving that you can relate one system to the other. And they already knew how to do that close to fixed points, close to periodic points. That's the kind of, the Hartmann-Grobman theorem gives a local version for that construction. And then the problem was, how do you pick all these periodic points? There are finitely many, but still there's more than one, and how you extend this to the whole ambient manifold. And that, in picture terms, meant how do you grow those lines? They are called tubular families. How do you grow the domain of those lines in such a way that when they meet, as they grow, they meet in a consistent way, in a coherent way? Jacob told me many times that everyone told him that it was impossible, it was too complicated. In dimension 2, that's fine, okay, you are going to be able to do it. When in higher dimensions, no way. He just didn't believe, and he did it. So he proved this theorem. Now, this is already the end of the 1960s, and at that point, through discoveries of various people, it was already known, as I said, that Morse-Smale systems are actually not a dense subset, except in low dimensions, except for Peixoto's setting. It was known that structurally stable systems need not be Morse-Smale, so this was not the right definition to capture the notion of structural stability, and that has to do with one of the most famous discoveries of Smale, which is called the horseshoe. And it was also known that structurally stable systems are not dense either. So there was a little bit of a mess of what. So Smale tried to organize that mess by introducing a class of systems that is more general than Morse-Smale, called axiom A, or nowadays we tend to call them just uniformly hyperbolic. It has a definition. There's the set of non-wandering points should be hyperbolic. Periodic points should be dense in this non-wandering set. The point is, Morse-Smale, a relatively small class of dynamical systems, a bigger one called axiom A, and the goal was to try to recover. Okay, Morse-Smale are not dense, but maybe this bigger class is dense. And very characteristically, Smale immediately conjectured that indeed this larger class was dense. And that was, again, false, but at that point no one cared. The notion was here to stay. So in a very crucial paper in 1970, Jacob, together with Smale, formulated what has become perhaps the most important problem in dynamics for a couple of decades, called the stability conjectures. They stated the conjecture that the characterization, mathematical characterization of structural stability is the combination of being axiom A, this condition that I mentioned, belonging to this class, plus something topological called a strong transversality condition. Not so important. So essentially, being structurally stable corresponds to being axiom A. And they also introduced, Smale also introduced a weaker notion called omega stability, which is similar. The difference is that in structural stability, you want the conjugacy to go from the whole manifold to the whole manifold. And in omega stability, you restrict yourself to the smaller set, the omega set. So it's analogous, but it's a weaker condition. It's implied by structural stability. And the second stability conjecture proposes a characterization for this a system is omega stable if and only if it satisfies the axiom A plus the no cycles condition, which was discovered by Jacob, in fact. It's formulated by Jacob. Okay, so as I said, for about 20 years or more, the stability conjectures were the main, the focusing problem in dynamics. And there was quite a lot of progress. In the 1970s, people discovered how to prove one of the sides of the conjecture. If your system is axiom A, then it is stable. So that was done by these people. Axiom A plus strong transversality implies structural stability. And you will see that the second name on the list is the one of Wellington de Mello, Jacob's first student. He proved this theorem on surfaces. And the way he proved it was by extending the tubular family's idea in Jacob's thesis. And he was able to apply it in this broader context. Jacob was working with more Smale. Here's axiom A, more general, but on surfaces, he took advantage of the fact that the space was two-dimensional to extend that technique to prove the theorem, this theorem here. And in parallel, Smale and two of his young collaborators, the students, proved that axiom A plus no cycles implies omega stability. So this is by no means trivial, but in some sense, historically, was the easy part of the conjecture. The conjectures are an if and only if. This is the direction that turned out to be easier. Now, then the work started to go backwards to prove the converse. And the first thing was to kind of dispose of this strong transversality and no cycles condition. Robinson proved that if you have axiom A and structural stability, then you have strong transversality. And Jacob, even before he finished his PhD, had shown that axiom A plus omega stability implies no cycles. So at that point, to finish the proof of these conjectures, the important thing was to be able to say structural stability implies axiom A, or omega stability implies axiom A. That was the missing piece, and it turned out to be the deepest of it all. And that was done initially. The key contribution was by Ricardo Magnier, Jacob's second student, who proved around 1986, and it was published in 1988, proved that structural stability implies axiom A. And of course, he was sharing this with Jacob. I attended some of their discussions. Jacob was trying to convince Ricardo that with what he had done, he should be able to finish the thing and prove that omega stability, which is a weaker condition, was enough for axiom A. Ricardo kept saying, no, it's not possible. I am not there yet. The methods are not there yet. So Jacob convinced him by doing it himself. And they published the two papers together, the same issue of the Publication Mathématique de l'IHES. So that was Jacob's contribution. And then, quite a few years later, Shuhei Hayashi from Japan extended the methods for flows. They were working on the diffeomorphisms extended to vector fields, and he did much more. He proved an abstract result called the connecting lemma, which had many other applications. Okay, so that is a very quick outline of Jacob's influence in the realm of global stability. Now, let me talk about bifurcation theory. And the first thing is, what is bifurcation theory and why should you study it? And the drama is the following. Smale, on many occasions, at least 2 occasions, tried to provide a model, a picture of how most dynamical systems look like. Most dynamical systems are more Smale. Here's the model, okay? Now, okay, I was wrong on that, my bad. Axiom A, a larger class, are most dynamical systems. And this was still not true, and to this day, we don't know what could replace that. But more about that later. So Jacob and other people, and they were inspired by work done here by Jorge Sotomayor, came up with the following approach. Look at the picture. Let's start with a dynamical system which is more Smale. Let's modify it continuously along a line, smoothly along a line. So this is a picture in the space of dynamical systems. C0 is a dynamical system, is a map, a diffeomorphism, or a vector field. And then you modify that along a parametrized family until you reach the boundary of more Smale. And then you ask questions. How do I leave? How do I go out? How do I cross the boundary of more Smale? So what is the structure of that C sub B, the bifurcation system? How does it look like? And most importantly, and what happens afterwards? Once I leave the relatively tame world of more Smale systems, what happens? What kind of dynamics do I see? How is it? What's the picture? So in a series of papers with Sheldon Newhouse and later Floristakens, they made various contributions. I cannot list them, but in particular, they defined the notion of structural stability for parametrized families of systems. They characterized it. They have a long paper in this Newhouse Floristakens 1983 paper. It's a very long paper in Publication Mathématique that I and my colleagues studied very intensely. And the interesting point, beyond the technical aspects of the statements, is that the methods that were used for developing this theory were, again, tubular families, an extension of the construction that Jacob had developed in his thesis. In his lecture 25 years ago, Sheldon Newhouse makes the point that in some other areas of this theory, the geometric methods that Jacob introduced have been replaced or have an alternative through more analytical methods based in spectral theory, etc. But in this particular domain, all that we have to this day are Jacob's geometric methods, tubular families, invariant foliations. Now, starting with systems that are in more Smale was just a starting point to begin the theory, but immediately Jacob started proposing that we should actually start, say, inside axiom A, inside this more general domain, broader domain, and carry on this theory for parametrized families. So now instead of more Smale, just think you start with axiom A and what happens afterwards. So how do you leave the domain? How does a dynamical system lose its stability? What are the mechanisms that can turn a dynamical system which was stable, unstable as you modify it along a parametrized family? So these are exactly the same questions. The difference is now that this C sub 0, the initial point, would be axiom A. There are many, many things you can do. And of course, Jacob went for the hardest one. he proposed to look at what is called homoclinic tangencies. Let me try to explain this picture. There's an interesting hyperbolic object here, H. It's the horseshoe. It's a representation of a small horseshoe. And the interesting thing is that one modifies, attached to H, there are families of curves called stable and unstable leaves, and one modifies these leaves by pushing until they have a non-transverse intersection. Transverse intersections are nice, they produce very rich dynamics. Non-transverse intersections were the mystery, and they actually are even nicer. They produce even more complicated dynamics. So the question is, suppose you start with a system which is axiom A, it has a horseshoe, and you modify it in this way. The moment you create this tangency, you are crossing the boundary of axiom A. That's a fact. The existence of this tangency is an abstraction to axiom A, to hyperbolicity. What happens afterwards? Okay? And as I said, the horseshoe has these two families of curves, the stable and unstable leaves, which are represented there. So in some sense, what happens afterwards is that these two families of curves start to cross each other, start to cut each other. Think of a bunch of parabolas sliding against a bunch of more or less straight lines, and that's what happens, whatever that means. Now, there was a previous result by Sheldon Newhouse. It was his thesis that he developed afterwards, which said that if you start with a horseshoe where these two families of curves are very thick, so there's a lot of curves. They fill in not the whole space, because anyway it's just a zero measure set, but they are very thick in some precise sense. Then as you make this, as you unfold the dynamics, you see the parabola type curves going through the ones that are more straight. If they are thick enough, it turns out that they are always having tangencies. It's not very intuitive, okay? But if they are really, really thick, as they move, they keep having tangencies. And each time they have tangencies, which is always, the system cannot be axiom A, cannot be hyperbolic. So in this way, Sheldon showed how to construct open sets of non-axiom A systems. That is something that they knew. Sheldon Newhouse was also a student of Smales, a bit younger academically. And so together with Jacob, we extended this. This was done by Sheldon for surfaces, and we extended that for any dimension in the 1990s. So this was on the background. This was the information they had. And Jacob realized that the way to approach this problem, that the problem had to be formulated in terms of fractal dimensions, of the house of what is called the transverse house of dimension of these foliations. Transverse house of dimension. House of dimensions are fractal dimensions, a number, positive number, which need not be integer. And by transverse, I mean that you cut the two foliations, the stable and the unstable, you look at the intersection, you calculate the house of dimension. So I represent them by du and ds, and it turns out, it's very nice, that the sum of these two dimensions is equal to the house of dimension of the horseshoe. So this, you see, this is not proving anything. It's just realizing that the way to approach the problem, the way to formulate it, was through this notion, which was not so familiar to dynamicists at the time. And through this, together with Palis, with Takens, with Flores Takens, they proved the following fact, the following theorem. If the horseshoe you started with has a dimension which is smaller than 1, then for most parameters after the tangency, you have axiom A. And that's what this formula there means. You take the Lebesgue measure of all the parameters for which the system is axiom A, and on some small interval, and that the measure of that set, the Lebesgue measure of that set, is approximately the length of the interval. So the axiom A prevails in parameter space as you go across this first tangency. Then, a few years later, with Yocos, he proved a kind of converse. Palis is about house of dimension being smaller than 1. Suppose the house of dimension is bigger than 1. Well, in that case, axiom A does not prevail. And it looks like just denying switching the quantifiers, but it requires very different methods to prove that in that case the limit is not 1. The lim inf is smaller than 1. Now, the main point is, what is behind these facts in dynamics? Because what is behind understanding the root for the proof turned out to be extremely fruitful. Behind the proof was a theorem proved by Marston in the 1950s. It's a theorem that has nothing to do with dynamics. It's a theorem about number theory. You take two Cantor sets, K1 and K2, and you look at their difference. There's a factor lambda, but it's essentially the arithmetic difference as defined there. And Marston observed that if the sum of the two, the dimensions of the house of dimensions of the two Cantor sets is bigger than 1, then this difference has positive Lebesgue measure. I give you 15 seconds to think about this. A Cantor set is a set with 0 measure. The other Cantor set also has 0 measure. You take the difference between the two. Okay, the difference in the sense that you subtract elements from one from elements from the other. And essentially, Marston says if the two sets are relatively thick, if they are relatively big in terms of fractal dimension, then the difference has positive Lebesgue measure. It's kind of magic. Start with two sets with 0 measure, look at the arithmetic difference, a very simple operation, and you get something with positive measure. So this was, I think, by discovering this theorem, Jacob knew that the theorem was true, and then he and Jean-Christophe worked out the proof, which is absolutely non-trivial, but it starts from this. Then Jacob became ambitious and formulated a conjecture which says for a class of Cantor sets that I don't want to define, that he called regular or dynamically defined, the arithmetic difference, there are two possibilities. Either this difference has 0 measure. Now there's no assumption on the dimensions, okay? So either the difference has 0 measure, or in fact, it contains an interval. Either it has 0 measure, or it has non-empty interior. So it's a much sharper thing than saying it has positive Lebesgue measure. Either it's 0 measure, or otherwise, typically, generically, it contains an interval. This, as a statement in number theory, is interesting enough. This is already quite some with implications in our harmonic analysis in other places. But of course, he had in mind implications in dynamics. And that was done by Gugu, by Carlos Gustavo Moreira and Jean-Christophe Yocos during Gugu's postdoc in Paris. They proved a very strong version of this conjecture, which gives a lot more information, and they extracted from that proof the dynamical consequences that Jacob had in mind. In particular, if you compare this with Palis Yocos, they had lim inf less than 1, and that's one byproduct of the theorem of Moreira and Yocos, is that you can actually write lim sup. A few years later, Jacob and Yocos introduced a notion that they call non-uniform hyperbolic. I prefer to write non-uniform axiom A, and they proved this result in the same spirit, which says that if the dimension is bigger than 1, but not much bigger, you can still get full density, limit equals to 1, but now you have to allow for the system to be non-uniform axiom A, so as a bit more general condition, and then you still get full density. Now, this was 2009, and this is a 217 pages paper. Okay, just to give you an idea of the level of sophistication, technical sophistication, and depth of the ideas that go behind it. It occupies a complete volume of Publications Mathématiques de l'HES, which is one of the most exclusive journals, 217 pages. I used to joke with Jacob that there's this story about the book of Russell and Whitehead, which has 2 co-authors, and no one read it completely. The Principia Mathematica I joked with Jacob whether his paper would be in the same condition. But he claimed he read it all. So. Okay. In the mid-1990s, Jacob was feeling confident enough to try to go back to the story, to the beginning of the story, when Smale was making all these attempts to describing how most dynamical systems look like. And he started developing a program. A program for the younger ones is when you ask questions and let your colleagues answer the questions. You transfer the work to the younger people. A program guiding, suggesting directions in which one could try to develop again a global model of how a dynamical system looks like, typical dynamical system. And one of the key ideas was that after all the work he had done on homoclinic tangencies, he believed that homoclinic tangencies, since they are so complicated, they are so rich, they should also be the kind of structure that we could use as a unifying concept to understand what lies beyond axiom A. Now, this, in higher dimension, dimension 3 or higher, there's a related phenomenon called heterodimensional cycles, which I try to describe here through a picture. It's having one or more, 2 or more points related by intersections of their stable and unstable manifolds. And the heterodimensional means that the stable manifold of the one is a different dimension from the stable manifold of the other. This is a theory that was very much developed by Lorenzo Diaz, who was also a student of Jacob's. So one of his focuses was this conjecture that every dynamical system can be at least approximated by one that is axiom A, and if that's not possible, then it can be then the fault is the presence of a homoclinic tangency or of a heterodimensional cycle. If you are unable to approximate your system by something nice, axiom A, then that's because there's a homoclinic tangency around or a heterodimensional cycle around that can be, that is causing that situation. The first and very big progress in that direction was achieved by 2 more students of Jacob, Enrique Pujals and Martin Sambarino. In 2000, they published in the Annals of Math this theorem. On surfaces, the conjecture is true. That's what the theorem says. The conjecture is true for diffeomorphisms in 2 dimensions. In 2 dimensions, you don't have to worry about heterodimensional cycles, so just focus on axiom A and homoclinic tangencies, and they proved this fact. Any diffeomorphism of a compact surface can be CR approximated by another which is either axiom A or has a homoclinic tangency. And then there were various developments to extend this theorem to higher dimensions. I mentioned a few. Sylvain Crovisier, who was a student of Yoko's and was one of the people that contributed very significantly to pursuing Jacob's program, proved 10 years later that any diffeomorphism of a compact manifold is approximated, and this is C1 approximation. It's a very important difference. I'm not going to get into the difference here, but it's a very important difference. In some sense, replacing these C1 by CR is one of the big challenges. So it's approximated by a C1, by a Morse-Mill diffeomorphism, or by a diffeomorphism which has a transverse homoclinic intersection, and so has a horseshoe. And perhaps the state of the art in this direction is the theorem of Sylvain and Enrique Pujals from 2015. Any diffeomorphism of a compact manifold can be, again, C1 approximated by a diffeomorphism which is essentially axiom A, or has a homoclinic tangency or a heterodimensional cycle. So what's the difference with respect to the conjecture? Two differences. One is the word essentially. Essentially, axiom A is a generalization of the notion of axiom A that I wrote here. It means that the diffeomorphism has a finite number of hyperbolic attractors, and their bases of attraction cover an open dense. It's a more flexible way of thinking axiom A, and perhaps not less interesting than axiom A itself. And the other difference is, of course, the fact that this is C1 approximation. But you see, this is a theorem that goes very much in the direction of Jacob's conjecture, and in the direction of his belief that we identified the two phenomena that are responsible, perhaps the only two phenomena, who knows, that are responsible for the fact that Morse-Mill systems, that axiom A systems are not a dense subset of all the systems. Now, in this program, Jacob had a second big idea, which is perhaps even better known. He believed that in most dynamical systems, no matter how complicated they are, the future, there are only finitely many possibilities for the future, finitely many attractors. So depending on the starting point of your system, there's a finite number of places where you can go to, and the key thing being that's the set is finite. And I remember a lecture where he was presenting this conjecture, and a female colleague in the audience asked him, what's so wrong about having infinitely many attractors, which we know also exists. And I think he was taken by surprise by the question. He said, well, if it may be that we cannot avoid that possibility, and that will just mean that our life will be even more interesting if we have to deal with that more complicated situation. But at least right now, it's good to believe that there are finitely many, because we can try to build a theory and understand those kinds of systems. So this is the conjecture, famous Palis conjecture on finiteness of attractors. There is a CR dense subset of all dynamical systems, such that any dynamical system in this subset has a finite number of attractors, and the attractors are nice. They have nice ergodic properties. In particular, there's this notion of physical measure. A physical measure is a probability measure on the space, which is invariant, and for which the basin is a big set, has positive measure, and the basin is just a set of points whose trajectories, the statistics of their trajectories obeys the measure mu. I mean, you don't have to get all the technical keywords there. I'm not even defining them properly. The point is, belief that there's, at least for a dense subset of systems, one has a finite number of these objects, and they control everything. And the methods, the theory, the techniques that we developed can be, in particular in ergodic theory, can be applied to them to understand what the dynamics is. So the one setting where this has been achieved in a very particularly deep way is the context of maps of the interval. the kind of maps this theorem refers to are the ones with a graph like this. It doesn't have to be a parabola, but think of a parabola as an example. And in 2003, Arthur Avila, Wellington de Mello, and Misha Lubitsch proved that for families of maps of this type, for any family of a family would correspond here to considering various parabolae moving with the parameter. Okay? For different parameters, you get different parabola. For any such family, or more complicated things, then almost every system, for almost every parameter, either the system is like the one I've depicted here, which has a periodic attractor, and most trajectories just go approximate this periodic attractor. In this case, it's a fixed one. Or they are stochastic, and stochastic has a technical meaning. It means that there's an absolute, a physical measure, which is essentially Lebesgue measure on some subdomain, an absolutely continuous physical measure. The theory that is behind this is much deeper. It gives much more things, but as a kind of important subproduct of that theory, called the renormalization theory for unimodal maps, one gets this very precise description. So essentially it says, for typical maps of the interval like these, either you have an attractor which is just a point or a finite number of points, or you have a stochastic attractor which looks like an invariant measure, but still something for which we have the theory to understand how they behave, how they evolve, how they bifurcate. At about the same time, I was working with initially with Christian Bonatti in Dijon, and then with José Alves from the University of Porto, and we looked at another class of systems more general than Axiom A, called partially hyperbolic systems, and we were able to prove a number of results, again in this spirit, within this ideology of Jacob's. We proved that under two fairly basic conditions called mostly contracting center or mostly expanding center, we proved that in both cases the diffeomorphism, the partially hyperbolic diffeomorphism, does have a finite number of physical measures, and they describe the behavior of almost every point in the manifold. And I mean, you have the conditions, you like them, but then of course you want to prove something more general. We wanted to prove something for most systems, getting rid of these conditions. And that was actually done by Masato Tsuji in 2005. He proved that for generic partially hyperbolic maps on surfaces, there are finitely many physical measures. The basins cover almost every point. So he uses a little bit of what we did and more ideas to get rid of the conditions. Either it's mostly contracting and I do this, or if it's mostly expansive, I do that, and if it's not, I do something else. So he was able to prove for generic maps on surfaces. One of my students, Riccardo Bortolotti, extended some of these results of Tsuji for higher dimensions, partially hyperbolic diffeomorphisms in higher dimensions. And that's just one example of the many, many examples of people that I did not mention at all, but whose academic trajectories were touched by Jacob's vision. And I wrote some of their names. Pedro Duarte should also be listed there, who was also a student of Jacob's. Ricardo, I just mentioned, Mário Jorge Dias Carneiro, Lorenzo Dias, Liao in China, Leonardo Moura in Venezuela, Carlos Morales, also originally from Venezuela, Gugu, Maria José Pacífico, Atsuro Sanami from Japan, Sebastian van Strien, Raul Ures from Uruguay, Lan Wen also from China. There are some of the people that were mathematicians whose production was touched by him. Thank you.